All right, so ladies and gentlemen, this is part two of our discussion on the idea of angular momentum. All right, just kind of review the first half of this video, talked about the idea that angular momentum is just this kind of quantity that objects that are spinning have, and it's the fact, just like normal momentum is an object wanting to keep moving forward. Angular momentum is the idea that an object wants to keep spinning in a very specific way. So we've got three practice problems that we're going to work through. And the first one we're going to do is this one is I have a discus and it's just spinning on top of my finger. And the discus has a moment of inertia. It's a disc, so its moment of inertia formula looks like that. And it's got a mass of 2 kilograms and a radius of 7 centimeters. I want you just to calculate right now, what is the angular momentum of that discus if the angular velocity is 4 radians per second? All right. And we'll remember, just looking at this, that the angular momentum is just equal to the moment of inertia times the angular velocity. So you're going to have to do a couple calculations, but I want you to pause the video, calculate that. Once you think you have it, it's going to be a weird unit, so don't worry about it. Once you think you have it, come back and we'll see if you're right. All right, so hopefully you had a chance to calculate that angular momentum. You first had to calculate the moment of inertia, and then you had to calculate, multiply it by its angular velocity. So in order to do that, you kind of use the moment of inertia formula, plug that in there, multiply by omega. So once you get that, and I apologize, I'm not really going to walk through that part. I'm very confident at this point we know how to plug things into a formula. You should get that when all said and done, the angular momentum of this discus is 0.0196, and here's the unit. It's really weird. It's a Newton times meter times Newton meter second. All right, and of course for the AP exam, you are not going to need to remember how to do this. And honestly, that number does not mean anything to us, and that's totally fine, because we're really just going to keep focused conceptually on the idea that this is just an idea of keeping things stable when they are spinning. So that leads us to the next question, which is you're actually doing the same thing, but you are not even using numbers. All right, so what I've done now is instead of using a discus, I've taken a ball that has the exact same mass and radius. And I want to do the same thing. I'm going to spin it on my finger. And I want you just to kind of look at it, and I want you to explain to me why, without having to use any calculations, how do I know the angular momentum of that object will actually be less than the discus was? So take a second or two, just kind of think about it. If you need to, pause the video, and then we'll talk about the answer. Right? So if you kind of looked at it and thought about the formulas, you'll notice that for a ball, that's a sphere, and a sphere has a different moment of inertia than a discus does. Okay, and now these formulas will be provided for you on the AP exam. More than likely, you're not going to need to use them at all, so I'm not worried about it. But you can see that the moment of inertia of a sphere is actually slightly less than the moment of inertia of a discus, which means that if I have the exact same parameters as everything else, the angular momentum has to be slightly smaller. All right, so we'll just say angular momentum of ball is less because this moment of inertia is less. All right, and that would be the equivalent of if we were talking about an object that was just moving in a straight line. That would be the same thing as saying, well, one object has less momentum than the other because its mass is less. Okay, so we're just thinking about this idea, ladies and gentlemen, of how angular momentum and moment of inertia are related. So the next piece, this is where we really see angular momentum come into play. And it happens a lot, all the time pretty much, in the universe. So let's say I have a dying star, and it takes approximately 15 days for it to make one rotation on its axis. Now that star has a radius r and a mass m. Now the star goes supernova, which means it explodes, and it causes a drastic change in how the star is going to look. So afterwards, whatever star is left over, in this case it's a neutron star, you start to see that the neutron star now has a much, much, much smaller radius, 0.0001 of the original radius, and a much smaller mass, 0.05 of the original mass. We want to figure out how fast is the star going to spin now. All right, and before we even answer that, I just want you to think about the fact that based off of that, do we think this star is going to be spinning faster or slower than it was previously? Hopefully, just kind of thinking about it and looking at it, you thought about the idea that this probably made the moment of inertia of this star significantly smaller, which means that it must be spinning significantly faster than it was before. All right. Now, this question kind of can seem complicated just because there's a lot of moving pieces going on. But honestly, what it comes down to is we just want to figure out first what the angular momentum of this star is at the beginning. So, this beginning angular momentum is just going to be equal. So, the starting angular momentum is just equal to its moment of inertia times its angular velocity. All right. The moment of inertia doesn't really say it in the question, but the moment of inertia of a star is the same thing as the moment of inertia of a ball. They're both spheres. So it's going to be 2 fists times m times r squared times some angular velocity that we don't really know, but remember, we can actually calculate that pretty easily because angular velocity is just the amount of radians or degrees I travel in a certain amount of time. And if the star makes one rotation every 15 days, that means it's making 2 pi radians every 15 days. So the angular velocity is going to be 2 times pi divided by the time it takes to do that. Now, of course, 15 days, I don't like it in days. I want to turn it into seconds. At this point, you know how to do that, I promise. And if you don't, this is a great task trying to figure out how I got to this number. But it's going to be that many seconds, 1,296,000 seconds in 15 days. So going through and doing that, you calculate that the angular momentum of the star beforehand is some number, but you don't actually get a full number because the mass and the radius are just variables. But what we can do now is we know this is the beginning angular momentum. So we say this has to equal the final angular momentum. So what we do is we now go through and we look at the fact that we know that the radius and the mass are significantly smaller now. We still don't quite know what it is, but we know they're smaller. So the mass is now, originally it was just a mass m. Now it's going to be still a sphere because it's still a star, but now the mass is going to be significantly smaller. And when we do the radius section, or the r section for the moment of inertia, we know this is way, way smaller. It's 0.0001 of the original radius. And that's going to be squared, so that's going to be an absurdly small number. All right. And then we're going to multiply this by the new angular velocity. Now, the issue is when all said and done, we want to find the new period, which just basically means how long does it take to go around once. So we can actually go back and we can use the definition of angular velocity, and we can say that the period that we're looking for is in that formula. So instead of saying the new angular velocity, we're just going to say 2 pi divided by the new period, because that's all it is. All right. Now, honestly, I want you to go through and do this math. I'm not going to go and highlight how to do all this, but if you go through and make the calculations and find the period, you're going to figure out that the new period, once you figure out the new omega, the new period is absurdly small. In fact, the period after the supernova is going to be about 0.00065 seconds. All right. Now, just to give you an idea of how fast that is basically, that's less than a millisecond. That is an absurdly fast amount of time for a neutron star to spin around once, but that's exactly what happens in the universe. And there are a lot of weird things that happen when stars die that give whatever's left over really fast spin. And if you're curious, feel free to watch a video I've linked in here. It talks about kind of black holes and spinning black holes and kind of what you can do with them. But it gives the idea that what happens to a black hole when it ejects most of its matter during a supernova.